Hi, good morning, everybody. Ladies and gentlemen, today we are going to have the second plenary speech. The first one is coming from the Professor Micki, who I knew from probably a couple of, 20 years ago or more than that. When I was a postdoc, I worked with Professor Micki, and at that time, I learned a lot from her to do some research on conceptual change. And today, I'm honored to introduce her to be the first speaker. And there are quite a lot of achievements Micki has done, and I probably need to use 45 minutes to name them. So I just want to highlight one of them, which is the distinguished contribution to research in education for the 2016, and congratulations. And I think that's really a big achievement. And next week, Professor Chi will give a great, long and complete speech at the AERA. So we are quite honored to have her here. So please join me to welcome Professor Micki.
Thank you for inviting me. I've actually never been to NARST, but maybe I can come more often. No. It's always along the AERA, so hard to get away. Let's see. So that's the session title. The session title is about challenges in learning science concepts. And in particular, I'm going to talk about teaching emergence and our attempt at trying to discriminate, teach students to discriminate different science concepts. So what is the problem in STEM learning? I think one of the problems that is pretty alarming that U.S. is really far behind in training students interested in STEM. And one problem just might be that they have deep-rooted misconceptions, as you all know. So deep-rooted misconceptions have been documented well over four decades. I've read it ever since I was in graduate school, and it's very ubiquitous in the sense that it applies to all concepts, all domains, and so forth, and all ages, and even in different cultural groups. And they persist and are very resistant to change despite the best instruction. So that's a very serious problem. So the research question I've been trying to address for several decades now, culminating in the more current work that I'm going to talk about today, is why are these deep-rooted misconceptions so hard to overcome? So the first goal is to try to provide a theoretical explanation for their existence and their persistence and so forth, and then to see whether we can come up with an alternative instructional approach, maybe a novel one that we haven't tried before. So throughout this talk, what I'm going to do is first talk about sort of the theoretical motivation that I've developed for the instructional intervention that we're going to eventually try. And I'm going to make a lot of assumptions in my theoretical analysis, but that's sort of necessary to make a complete story. So what are misconceptions? What I propose is that there are really two ways, two kinds of misconception we can think about. And we can think about them as two kinds in the context of how they are incorrect. So a misconception is an incorrect piece of knowledge that could be incorrect from the normative perspective, that is, from the perspective of the expert knowledge, and we can think of that as incorrect in the true-false sense. Or it could be incorrect in the ontological perspective, which I will explain, which means it's incorrect in sort of the incommensurate sense, and I'll explain that in a few minutes. So what is the ontological perspective? So typically, categories, we think about categories as hierarchically related, right? So animals is part of natural kind is part of objects, and so forth. And psychologists, for example, always study the subset-superset hierarchical relationship. However, we can also think about categories hierarchically. That is, sometimes I call it laterally related. Nobody knows what that means. Anytime I use a word that I define, I put them in quotes. Lateral categories are ontologically distinct. That is, for example, entities and processes and mental states. You could think of them as ontologically distinct. So what does ontologically distinct mean, or incommensurate? I'm going to give you an example by running through this car example. So basically, two concepts are ontologically distinct if they cannot be described by the same dimensions or predicates. So it's not a matter of whether it's true or false on a value and a specific dimension. So let's go through this example. So how can we tell that this car, which is an entity, and a car race are incommensurate? How can we tell? By showing that the dimensions of one concept cannot be used to describe a member of the other category in a sensible way. So because the car is an object or entity, objects have dimensions such as weight, color. It can be contained inside a box. So therefore, it's false to say that the car shown here is blue, but it's sensible, that is, it makes sense, because a car can have the dimension of color, even though the color is incorrect. So it's in that sense incorrect in a true-false sense. But to say that the car happened yesterday or that the car is sad is anomalous. It doesn't make sense, because these predicates are dimensions of processes, which is dimensions of time, and mental state, dimensions of motion, let's say, which are not dimensions of objects. So a car and a car race, on the other hand, is obviously a process. You can say the car race happened yesterday. So a car and a car race are concepts that belong to two ontologically distinct categories. That makes sense, I hope. Okay. So let's illustrate the distinction between incorrect and true-false sense versus incommensurate sense. So these are actual quotes from students. Suppose you ask students which cup keeps the coffee warmer, the styrofoam cup or the ceramic cup. This is work that my former student Jim Slaughter had done. And one student might say the ceramic, which is false, and another student might say the styrofoam, which is true. But if you read their explanations, the explanations have one thing in common. One student might say false, the ceramic, because the heat's going to escape. The other student might say styrofoam because it would trap the heat. So regardless of the accuracy of their responses in the true-false sense, their explanations are incommensurate with the correct explanations, that is, in terms of the ontological predicates. So using predicates such as going to escape or trapped describe heat. It's treating temperature as a measure of the amount of hot molecules, which is the entity notion, that can be trapped, right, versus the speed of molecular motion, which is a process notion. So the first assumption I'm making is that misconceptions are instances in which a science concept is miscategorized into an alternative ontological category, and I just gave you the heat example. Why is this miscategorization a detrimental problem that is preventing conceptual change? Well, it turns out categorizing is one of the most powerful human abilities that, for example, psychologists have studied for decades. What it does, for the two advantages it has, is that it allows you to reduce the complexity of the world, right? You can categorize things and make sense of it more easily. But the second thing that happens that people don't talk about as much is that once a concept is categorized, that concept inherits all the dimensions of that category. So this inheritance property, which is really, true and prevalent, turns into a disadvantage if a concept is miscategorized into an alternative category. So you can see how serious that can be. So you inherit all these dimensions that are inappropriate. So correct categorization is critical to understanding and must occur prior to learning a lot of details about the concept per se. So note that in standard instruction, we typically confront the incorrectness of a misconceived explanation. That is, we take the normative perspective rather than challenge the categorical dimensions of a misconceived explanation, that is, the ontological perspective. So what is the challenge in re-categorizing? Previously, I've called it shifting, reassigning, if a concept is initially miscategorized. For example, children often think that whales is a kind of fish. It can be easily refuted and reassigned to that whale as a mammal. The reason you can reassign that easily is because students are very familiar with the category of mammals, right? But the fact that they can't change conceptually for misconception suggests that maybe they're not knowledgeable about the alternative category that is appropriate for many science concepts. So that's the implication. What is the appropriate alternative category then to which a misconception belongs? So in prior work, we had assumed that misconceptions are concepts that should be categorized as processes and not as entities, right? So this unidirection suggests that you always misconceive process as an entity and not the other way around. This unidirectional misconception suggests that students might be less familiar with processes per se, and I'll talk a little bit more about that later. Okay, let's go. So we had assumed, let me make sure we had assumed that heat, earlier we talked about, has been conceived as entity. So it's shown, the right part shows the misconception that is, if you have two bars, a hot bar and a cold bar, they think that hot bar has more hot molecules and cold bar has cold. I mean, this is just one form of misconception, and they're all very similar. But what is their misconception about heat transfer? Because surely they talk about heat coming into the room, cold leaving your room if you open the window. So it seems like it wasn't sufficient to claim that misconception of process as an entity was the complete story. So that was a problem that I was stuck on for a long time. So what happens when you ask them about heat transfer? Well, basically, the misconceptions on the right, when they talk about heat transfer, what they all in fact talk about is hot molecules moving over and the other molecules moving back. So they have the idea of an exchange, their idea of transfer and exchange. So exchange location is a process. So what is the misconception then? I was stuck here for a long time. Okay, so we did additional analysis, suggests that we need to consider different categories of processes. So based on this analysis, we propose that processes can be decomposed into two ontological kinds. Let's just call it sequential and emergent. So misconception is misconceiving of, misconceiving emergent as sequential in that unidirection, but never the other way around. The fact that it's never the other way around, again, suggests that maybe students are unfamiliar with emergent processes. So we need to teach them a little bit about processes, right? So what are processes? There's very little scholarly work on what processes are. For example, psychologists typically study concepts of entities, right? What is furniture, what is animals, and so on. Or the only processes they study might be narratives and scripts. You can't even find the term processes in the index of a science textbook. So according to the dictionary, a process is a series of actions that produce something that lead to a particular result or a series of steps. I think of this as a definition of procedures. So it's much closer to the definition of sequential processes that we'll be talking about. We propose that processes can be described by three components. At least this is a starting point where we're starting to think about what processes are. The three components are the pattern that can be seen over time, the agents producing the pattern, and the interaction of the agents. So using these three components, we can describe a process as a series of interactions, not actions, among the agents that occur over time. And these interactions display a pattern. So what is the pattern of a process then? A static visual pattern is any static percept that you recognize and can interpret. So two people standing there is a percept, is a recognizable pattern. A circle is a pattern. The visual pattern of a process, however, is a changing static pattern, or you can just call it dynamic patterns. Many patterns are familiar to us and familiar to students and young students. There's a pattern of increasing size that we're familiar with, increasing height, increasing everything, such as numerosity, speed, color, location, direction, and maybe waves and spirals. These are all patterns that we sort of recognize. So patterns need not be visual, right? It can be auditory, somatic, or most importantly, it can be imagined. You can imagine evolution, for example, the pattern of evolution. So let me give you a couple examples of how we identify pattern or talk about patterns to students, the agents and interactions. So in this example of the process of wolf hunting, the agents are the wolves and the prey, that is, agents are the ones who participate in interaction. The interactions are wolves chasing prey, so chase is an interaction between a wolf and a prey. The pattern the wolves produce is sort of a go-directed path, going in the same direction. How about in the ants' foraging process? Who are the agents, the interactions, and the pattern? Agents are the ants that are looking for food. Interactions are ants either sniffing pheromone, dropping pheromone, and so forth. And the pattern the ants produce when foraging looks like a go-directed path in which the ants knew where to go to get food. So the process of ants foraging for food and wolves hunting for prey look very similar at the pattern level, both exhibiting go-directed behavior. So we claim that because the pattern looks similar, the causal explanations for how the go-directed path occur are similar. That is, attributing the cause to a single leader, in this case, like an alpha wolf. So the explanation for the ants is misconceived because the ant line is not formed by the role of the leader. So now that we know what the pattern agents and interactions are for processes, what is the problem? So let's look at this diffusion simulation for a second. So for something like diffusion, as you know, so the pattern level behavior is directional and seems intentional, stops at equilibrium. And the pattern, the agent level, is it can reverse direction, it's random and continuous. So the behavior of the pattern is very different from the behavior of the agents. So the problem is students cannot explain or reconcile how the pattern emerges from the agent's interactions. So I refer to this problem as the interlevel causal explanation, which is distinct, very distinct from learning more about the agent level. That is, you can learn the structure, function, behavior of molecules. Very different from learning about the pattern. That is, you can talk about the parameters that define the rate of flow. You can change the opening for the flow. Those are all parameters that affect the pattern level, and distinct from everything else. So learning such detailed knowledge about the pattern level or the agent level is often misinterpreted as having repair misconceptions. So if you look at some of the misconception research, if you look at the assessment questions, if this is what they measure for assessment, then actually they've gotten more knowledge about the pattern level and the agent level. But what they really haven't gotten is whether student actually can give better interlevel causal explanation. I know we've done the same thing. Okay, so what we did was, just to confirm whether what I'm thinking is correct, we looked at the misconception items across 9 concept inventories. And it turns out, on average, for physics, biology, and chemistry, for quick coding, the sample, on average, 41% of the questions are interlevel questions. This is in part why students never really can learn and do better on a lot of concept inventory, even though they have the best kind of instruction. Okay, if misconception results from not understanding interlevel causal explanation, then we need to explain the difference between a correct and an incorrect interlevel explanation. So to do so, we analyzed students' misconceived explanation across many concepts, which resulted in identifying several characteristic of their misconceived explanations. So I'm going to illustrate these characteristic attributes, that's what I'm going to call them, for the differences in the interlevel causal explanation. So suppose you ask students for an explanation, interlevel explanation. How do these geese come to fly in this formation? So typically, a naive explanation that a young student especially might say, or an older student, is that there's a leader goose telling the others where to fly. This one explanation alone implies the following attributes to me. So you could say what it implies is that the patterns caused by the leader goose, which is a single goose, or subset of goose, telling the others where to fly. The leader goose has greater control or centralized control, a more important role or special status. The direction that the geese fly tend to align with the direction of the pattern. And the V, so their V is intentionally formed, and sometimes I call this, they have a global goal. They want to form this goose, this V pattern. And finally, the lead goose would stop telling the other geese where to go once their V pattern is formed. So that one explanation implies these 5 attributes. However, they probably give that kind of explanation because they borrow it from an explanation for the airplane. However, for something like pilots flying in this V formation, the pattern is caused by a single agent. It is caused by a single agent or subgroup of agents like pilots and co-pilots. And so therefore, these agents do have special status. The direction is often aligned, that is, the plane doesn't go in the opposite direction when they're told to go in this way. And they have an intentional global goal. That's what I call the intentional goal. The lead pilot has an intentional goal of forming this V pattern because it is the best way to fly. And then once the pattern is formed, the pilot no longer needs to tell the other ones what to do, so that interaction stops. So, in contrast, how this pattern is formed that we talked about is exactly the opposite of what we just proposed. That is, the geese just wants to fly, each individual goose wants to fly in a pocket of least air resistance, let's say. And so the characteristics for these characteristics for this kind of explanation, exactly opposite of the one for pilots. That is, all the goose are doing the same thing, they have equal status, they're not, sometimes they are not aligned what the individual goose do, and the V is formed unintentionally, or they only have local goals, and the geese will continue to keep on adjusting continuously even when the V is formed. So we've got these 2 contrasting sets of attributes that we've identified that we're pretty confident that they do characterize these 2 sets of explanations, the sequential ones and the emergent ones. Okay, we propose that many science concepts taught in middle school and high school are a kind of emergent processes. That's our big assumption. And that students misunderstand them by treating them as similar to sequential processes. When we've talked about diffusion flow as water flow or heat transfer exchange of location. So it turns out that many science concepts taught in the middle school, which students are misconceiving, are emergent ones, the way I've characterized them. In fact, they're often in the same chapter, right? And they are not differentiated. So because of the unidirectional thing, we assume that people have a predisposition or bias to view processes as sequential. For example, the evidence is that young children can understand narratives, which is sequential, and misconception is unidirectional, as I said before. We interpret this unidirectional thing of the bias to mean that students are naive about emergence. So if this assumption is correct, that students don't have this knowledge, then we ought to teach them to learn about emergence so that they can use it to interpret and understand emergent life science processes in the school curricula. So, our novel instructional approach and goal. Our goal is to teach students about this category of emergence by developing an online module. We want to specify the similarities among processes, between both sequential and emergent ones. We also want to specify differences between them, and we want to do so by using everyday examples so that they don't have to learn the details of the science processes at the same time. And then we want to test whether this understanding of the general process module about these 2 kinds of processes can transfer to improve understanding of specific science concepts such as diffusion and natural selection. So besides the need to teach processes in general, the pattern agents and so forth, we face 4 significant challenges in developing a process module about both sequential and emergent processes. First, students need to discriminate the 2 kinds of process, right? Because they look similar at the pattern level. How are you going to teach them to discriminate them? Unless they can discriminate them first, they won't know which kind of explanation is correct. Then how do they overcome the learning paradox, which I'll explain in a minute? How do you teach them the mechanism of aggregating, summing, and how do you foster transfer? Very significant challenges. The question mark means that we haven't done that at all, and the bold question mark means we're really having a problem with that, or we have to confront that. Okay, the first challenge is, how can students learn to discriminate them? So it turns out the assumption we made is that you can actually discriminate them based on the features, I'm going to refer to features of the interactions of the agents, right? So, for example, for two kinds of processes, the interactions are very different. And the one kind on the left is on the left, the ant one, all the interactions are mostly the same. That is, all the ants follow the same rules. But for wolves, the interactions among the agents are different. Some are chasing, some do the killing, and so forth. And then, of course, for the one on the left, there's random interaction, and then for the right, it's more restricted. That is, the alpha wolf only kills the prey normally, doesn't kill all the other ones. So they have restricted who they interact with, whereas the other one, the interaction is random with who you can interact. And then there's also the issue of the interaction can either occur simultaneously or sequentially in the sequential process. So with these four features that we've identified, we can teach students how to discriminate this kind of process by looking at the interaction. So, for example, based on some tutoring interview type of work, we have streamlined and decided that we want to use these 5 everyday processes, pair processes, to teach them about these features. And then we're going to do a training test pair on one of the ones on the below. So just an example of the kind of everyday processes we're going to use. So how do we do this? So we actually will teach them to discriminate by pointing out, we could scaffold them, for example, point out that, look at what the pilot's doing, right? The lead pilot's doing something different from the other pilots. Look at the goose flying. The different goose are doing the same thing. So we can prompt them with scaffold. That's one approach we've tried. A second approach is to use this very complicated augmented phase diagrams. We've tried that too. So we're just still exploring a lot of methods. The second challenge is the learning paradox. That is, what is the learning paradox that Bereiter wrote about in 1985? Scholars all agree that learning is basically by assimilation. What does that mean? What that means is that we activate prior knowledge we already know about something related to it, and we embed this new knowledge with our prior knowledge, and which suggests that we can only form new ideas that's analogically similar, right? Because if you always embed it, then you're just expanding what you already know a little bit. So, but if learning is by assimilation, how can we ever learn anything totally new? That's the paradox, since if we don't have prior knowledge about emergence to embed it with. So, how can we teach something, especially something ontologically distinct and dissimilar? So to allow for assimilation to take place, that is, you want to be able to build from what you already have, what we're going to do is activate students' prior knowledge about sequential processes that they're very familiar with, the features and attribute, and then linking this to new knowledge, building it from it by using the concept of opposite or contrast. So by contrasting, we're actually linking by using the opposite link. The third challenge, how do you teach the interlevel mechanism that causes a pattern? So misconception, as I said, occurs when the same or similar pattern can be explained by 2 distinct causal mechanisms. We call one the additive cumulative summing mechanism, the other one, which is very familiar to students, and we call the other one aggregate collective summing mechanism. And they require adding all of the values at a given point in time, the idea of net effect. So let's say we give children students example of this kind. So you have a pattern here that you're familiar with. The pattern is increasing in numerosity. From day 1, you have $2, day 2, you have $6. So Joe has more and more dollars. What's the mechanism that can explain this? Well, what mechanism can explain it, in this case, depends on the context. So if you were going to the bank and depositing money, then the interactions are simply Joe depositing money every day, and the mechanism is he adds an amount to a prior day's amount, right? He simply adds what he had on the prior day. So I just call this cumulative summing or additive subtractive summing. You add what you have today to what you have prior day. And this kind of mechanism characterizes sequential processes. What if the context is Joe playing blackjack in those days? How do you explain his pattern of increasing dollars? Well, you can explain it by saying that every day he played blackjack, and at the end of the day, you sum all his wins and losses, and that's how much money he got. So this type of mechanism could characterize emergent process. Here's another example. Here's a pattern. You see a pattern of increasing number of people over time who knows about a rumor or a snowy day. On day 1, you have 16 people. Day 2, you have 26 and 36, and day 3, you have 50. How do you explain that? Well, in the context of an old way of connecting with people, you spread the news by a telephone tree, right? The first person calls 3 people, the 3 people call more and more people. So the increase in number, not dollar, is additive at each level of the tree. Some number of people are added to the prior day number of people. But in the context of rumor spreading, each person tells another person that they happen to run into, resulting in the same increase in pattern, but the mechanism is a proportion increase in the number of people who know the rumor over the number of people who don't know. So the idea of proportion is the idea of a collective summing. So we can discriminate that a telephone tree is a sequential process, but not only by the process, for example, by the features, such as different people do different things, and they're restricted, who you call is all well-defined and restricted. With rumor spreading, you can also discriminate using those characteristic feature I mentioned. Everybody does the same thing, and they can interact with any random other. So one is additive increase, the other is proportions increase. So they have very different causal mechanisms. So our assumption is that students are very familiar with cumulative additive mechanism on the left and not familiar with the collective mechanism on the right. And there's some characteristic differences in them that I haven't really given too much thought to yet. So in diffusion, not only they cannot give the interlevel causal explanation, but again, they don't know the mechanism that causes the perceived pattern. And the mechanism is proportion change from time 1 to time 2. The number of ink molecules, the proportion of ink molecule changes over time, gives you the visual perception of flow. And so, same with this kind of misconception that McCloskey writes about. It's in, I think, forcing concept inventory. They make the wrong kind of projection, and what, in fact, you have to do is get the net sum velocity for each point in time. So the toughest challenge, how to foster transfer of understanding processes to science concept of processes. You have to ground or instantiate the to-be-learned science concept in the context of emergence, right? So we tried this once, in which 8th grade students learned an overall process module that described emergent sequential, and we grounded it by instantiating in a particular way. This is the only way we tried so far, by using scaffolding prompt. Let me just show you the 2 conditions. So the experimental condition and the control condition had everything identical except for what is in red. So the experimental condition had a general process module. The control condition had a nature of science module that we just took standard nature of science. And then they had diffusion text. They have a macro simulation of diffusion, which is identical to the one I just showed you, and identical between conditions. And they have a micro simulation diffusion. And so the only difference between the 2 is how we prompt them in the micro simulation. As I showed you earlier, in the experimental condition, we prompted them with what we call emergent prompts. For example, a question like, we point to the molecule. Remember, we went backward. We said, can this molecule move in a different direction from the flow of the ink? Follow this molecule. Or we can prompt them with a very generic prompt, that is, describe how this molecule is moving. That's the only difference. We had pre-test, post-test. And this board gets published before, and this is our first try. And not only did we see, well, both groups improved, right, because we had very good diffusion materials, but the emergent group had additional 1 standard deviation more learning compared to the control group. So that's very promising. So I'm going to conclude by saying that our instructional approach, I think, is different and novel. It's very close to 2 other sets of research. One is complexity researchers' approach. So complexity research, their goal is to, I think, have students understand complexity. So they teach principles underlying complexity, such as dynamic equilibrium, feedback loop, self-organization, and so forth. The misconception researchers' approach is also different. They want students to understand science concept, so they teach correct science stimuli, right? And that's basically what they want to do. Of course, we also have different pedagogical approach, right? One is use confrontation, and we use compare or contrast and everyday example, so on. But basically, I think our method is a little bit different from the 2 because we're teaching knowledge of categories, we've identified characteristics of categories that we're going to teach, the attributes, the components of processes, and the interlevel mechanism. And so the outcome, we hope, is the fact that we can achieve some kind of transfer, that after you learn this, you could transfer to learning different domains, different concepts in different domains, like natural selection and heat transfer and so forth. That's what we're currently working on. And various people, this is a big project, so various people have helped out. You know, often different people come through my lab. My lab is called Learning and Cognition Lab. And thank you. That was fast, I know.
Yeah.
But I had to do it fast.
Yeah,
I didn't want to take time from Stella.
Yes, yes. Thank you for the profound speech. That was wonderful. You know, we tried to catch up your speed. You know. Okay, so Micki is very generous to give us 10 minutes Q&A. So now you have the floor to ask the question, and your speed of speech probably should catch up hers. Okay. So we could have as many people
Oh yeah,
as
I
possible.
wrote down my email, so you know any ideas you have, we'd love to hear about it because it's a very, very hard project, right? Yeah. So very tough.
And we will also post the video on the NARST website. So, you know, in 1 or 2 months, then you should be able to see the videos. And we have Randy here to help us to video. So, any questions? We have 2 microphones on the aisle, so. Oh, yes, please. There is a microphone. Yeah, go ahead. Because the light is very small.
Good morning.
Yeah,
Thank you for a really, really fascinating talk. I try to assimilate it into my old conceptions. It's not easy, so I have 2 questions. One is you were talking about assimilation and then the opposite. And I wonder what is the difference between this and what we know from our older knowledge about cognitive conflict and accommodation.
So wait, there's the resonance. What exactly is the question? The microphone. So there's resonance in when you speak.
So
What's the question?
Should I ask again?
Yeah.
Sorry. Okay, so you were talking about the issue of assimilation,
Yeah.
and then about the opposites that are the way to kind of like grow.
Yes, to link them, right.
And I was wondering what is the difference between this new knowledge that you presented and the old Piagetian concept of cognitive conflict and accommodation?
Oh, so cognitive conflict is probably a way to tell students that there's a conflict. Well, once they know there's a conflict, there's probably not. They don't know quite what to do with it. Where I'm the opposite, it's just a way to link or assimilate that knowledge by using the link of opposite. So one is an instructional approach. I guess the other one is an instructional approach. One is a way to allow you cognitively to link something because to assimilate, you always have to assimilate. So you have to have something to assimilate it to. So, but it's so ontologically different. How do you assimilate to something that's totally different? So you introduce the idea that it's the opposite. It's just a way that we're trying. I don't think anyone has tried that before. That's a good question. Anything else? I know it's fast. Huh?
There's another thing.
So I, first of all, want to say I think this is very useful work, can help us as science educators be more precise about how learning can occur. As you were going through your heat transfer example, I kind of had a worry that I want to bring up about how that learning worked. It seemed to me that the idea of randomness, I was thinking, is that really either necessary or sufficient for learning that the transfer is that of energy and not substance? So another way of saying is, it seems like I could have had a phone tree idea of how the transfer occurs and get pretty far with understanding that it is a transfer of energy. And then on the other side, I do need to understand that there's something that's transferred there that's not a substance. And so it seemed like the focus on the randomness wasn't necessarily all that you needed to do to make that occur.
Right. I'm talking about transfer. So this transfer is used twice. It's used in the context of heat transfer, which is a concept you know about. And it's also used in the context of transferring what they've learned. The way I've been using it is what they learn about emergence. Can they transfer that knowledge to learning about heat transfer, let's say? And the randomness, there's several aspects of random people talk about. So what the emphasis that I want to put is you don't just talk about, or students easily understand randomness in terms of what a single molecule can do. You have random actions, right? You can bounce all over the place. But what I needed to emphasize is randomness in who you interact with. So molecules can randomly interact with any other molecules, but obviously the ones closer by, they'll interact with. Same as rumor spreading. Whoever you happen to bump up to, you might tell the rumor. So there's no restriction. Whereas for sequential processes, there's often restriction of who you may interact with. So the transfer was used in two different ways. I don't know whether they answered your questions, but okay.
Okay, probably last.
Shall I take this way?
Hold on, here's the last one then.
Hi, I have a question about the slide that you showed with the bomb falling from the airplane.
Yeah.
And I was wondering if you could talk a little bit more about how you view that as an emergent process.
Well, the only part of that, well, one of my colleagues is going to talk a little bit more about that, I hope this afternoon, yeah. The only part of that is, that's not, I don't think about that as it's an emergent process only in the sense that it's a result of collective summing of the velocities at each point. So they don't think about that. I mean, that's the only application I can think of immediately, but I wouldn't call that the same kind of emergent process as the other kind, although you could think of the three forces or velocities as a summing thing. So it's only the mechanism of summing that's applicable there.
Okay, good. Please join me to thank Professor Micki Chi's talk.
Thank you.
Thank you very much.